Okay, so welcome back to part 2 of the recursive data structures session. Is anyone here who hasn't seen the first part? Okay, no problem. The second part is more interesting, for my opinion. But anyway, so just for a recap, we in the first part we had some definition stuff like what trees are and how we can store them, and where the comparison of client-side recursion versus server-side recursion. Maybe I'll just go back to this slide 4. There you go. So this was basically the first part was about general tree stuff, and we looked at some recursive store procedures, and we looked at nested sets. As I said before, nested sets can be really awesome because they're incredibly fast, but they can be a nightmare to maintain if you do it wrong. And so it really depends on how your data is structured and whether you have read-only data or data with lots of inserts. It depends. But in a lot of cases, if you combine them with classical trees, nested sets can be really awfully fast because, as mentioned, they're non-recursive retrieval of tree data. So can't get any faster than that. Even CTEs are not quite as fast. So I found with my experiments that the difference is really very small because recursive CTEs are also very, very fast. Okay, let's continue here. Has any one of you worked with CTEs so far? Common table expressions? Only a few. That's a shame. It's very powerful stuff. Okay, I'll do this the other way around now. I'll start off with the cons and pros, so we can concentrate on the real thing later. Cons of CDEs, recursive CDEs, that obviously, since you do everything from the client side, it's not a client-side recursion, but you select the query from the client side, the client obviously needs to know and understand the tree structure. So that's just the opposite of recursive storefronts, where the server needs to know the structure, the client doesn't. And here we have exactly the opposite. And one thing is that you have no complete PSQL command set available because it's just a select. So this is really for retrieving tree data. It's not for managing tree data like inserts, updates. But if you use a classic tree structure where you have a child record pointing to a parent, it's no magic to insert nodes or delete nodes there. So what we mostly care about is big, fast selects. And we'll see that in the practical examples later on. Just in amount of SQL text, they can become quite big. But so can recursive store procedures, so this is not really a common argument. Now let's look at the pros. That's rather simple. Just about anything else is a pro in CTEs. We have the server-side recursion that we wanted, so we don't have this to and fro. They're very fast. They take few round trips. Basically, it's just you send one select and get all the tree data back in one go without any further interaction. And with only actually two prepares. They're very flexible, very dynamic. You can completely control everything that you do with CDEs from the client side. And by that, they're completely transparent to the client because you send the entire statement from the client, so you can change it anytime you like and generate other statements. So you have complete control. They're also relatively easy to do once you get it, I must add. The first recursive CTE write will probably take you a while, but once you've done the second and the third, it's just like a snap. It's really easy. One big advantage that they have for me is they don't require any metadata changes. So if you need a different traversal of tree structure or different tables that you select the data from, you just change the SQL you send from the client, but you don't need to change anything in the database. This also includes that you don't need grants to those recursive store procedures if you use those. I mentioned before, of course, you need select grants on the tables that you get the data from, but you don't have any persistent database objects involved in those CDEs that you need special grants on. And since they're just an extension to the select statement, you can, of course, if you want, also use them inside store procedures. So you can really write a a recursive store procedure that is recursive not by calling itself, but by using recursive CTE inside. Okay, since I already thought that only a few of you have worked with normal CTEs, let's give a short introduction to those. Basic syntax is, first of all, you have a plain good old select statement, let you know it. And then you have what the documentation calls a preamble. So you write something in front of that select statement and can use that as part of the select statement. So the CTE has an alias name. So you say with my CTE as, and then you get the CTE definition, which in itself is just a select statement that returns data. And it's a bit like a derived table, if you've heard those. So once you define this alias, in the select, you can just select from that alias. So it's a bit like a view that you define inside your select. This is the most simple form. There are some others. One is not recursive, but I want to show it anyway because it really unleashes the strength of those CTEs. You can do something like this. You can have two CTEs in one statement. CTE1 as one select, CTE2 as a completely different other select, or maybe a similar one, what you need. And then you can do, in your main statement, you can do a select from those both CTEs. And you can, for instance, you can join them, or you can combine them in any other way, or union them, or whatever you want. And this is not limited to two. You can have as much as you want. And that's really one thing I find the strongest part of CTEs is that they're chainable. Actually, what you can do in CTE2 is you can select from CTE1. So you can drill down to your data. You can start with a rather general CTE that gives you a lot of data, and then you put a second one beyond that that just extracts the data you need. And if you want to refine that further, then you just write a third one below that that selects from the second one. And finally, you select what you need from either only the last one or from all of them, no matter what.
What is the main advantage of that?
It helps you think along with what you're doing.
Well, but that seems pretty similar to derived table, isn't it?
Yeah. Okay. So this is actually what you can also do with derived tables, but I find the syntax easier. It's a bit more transparent to me what you're doing there. So it's mostly, I can't really tell whether it's completely compatible. You would have to ask Vlad, he knows, but he's not here at the moment. So, but I think they're easier to handle and to write. So, and they can be recursive, which derived tables can't. That's what we're getting at now. So, just to make this perfectly clear, because I did a test run of this presentation for my colleagues, and they were like, but where do I define these CTEs? They are not defined anywhere. They are not metadata objects. They are just a part of one select statement. So this is all that you see there is one select. So what about the recursive CTEs? As we saw earlier on, a normal CTE you can think of as just an inline view declaration. It's just like you define a view and do a select from a view, except that you do it in one statement. Now the key feature of recursive CTEs is these CTEs can reference themselves recursively. And even if you forget all that I said here, this is one sentence I want you to remember. Recursive CTEs can recursively traverse any tree structure with a single on-the-fly constructed select statement from the client and very efficiently. Good point, good stuff. Okay, let's see how this basically works. First is the magic keyword with recursive. So you don't just write with my CTE alias, you write with my recursive, with recursive my CTE alias as. Then you do one select where you select the parent data, the parent node. Then comes the magic union all, which is obviously give me first the result of the first select and then just attach the result of what comes now. And then you do a select for the child data. And now the whole trick about CTEs is somehow the server has to know how the child and parent nodes are interlinked. And you do this with a plain good old join. So here you see you join on the thing that you're just defining on the join condition is just my child ID master is my master's ID. And then you have to close the bracket, and I always write a do there because I'm a Delphi programmer, and after with there has to be a do somewhere. But it's just a comment, it's not needed. Okay, then you can just go and select anything you want from your alias. And of course, here you have the complete feature set of a select. So you can do subselects and joins and order bys, group bys, whatever you want. The rest is just ordinary select as you know it. Okay, so let's see how we can do this file system example we had earlier on, where I used the recursive store procedure to retrieve the tree of the file with a CTE. We had the structure that we had an ID and a file name in every node, and we also had the ID of the master node stored in each child node. So this is our anchor, our recursion anchor, that's the top node, the root node. And you just need a condition how the server can find that root node. You can also put in a parameter instead of that 0, and just prepare the statement, put it in the parameter, and execute it then, just like with any normal select. Then we have our famous union all. And then you do the same, basically, for the child node. I just give this an alias here so I can keep them apart. I don't know whether it's really required, but I think it's more understandable what's happening here. And you just join this onto this on the condition that the ID master of the child node must be the parent, which is this here, PA ID. So this is what in the slide before I had as the parent link. So this is really the link that you're making here, from the parent's ID master to the parent's ID. And then again, of course, our select from. So let's see if this really works. So here you go. This is more or less exactly the example from the slide, just with a different alias name, but it's same construction. So we got this join here on the ID master. And if I just run and execute this, you see we'll get exactly the same result as we had with the recursive store procedure, but with a single statement from the client. Okay, now let's look at what actually happens in the server when you do a recursive CTE. It's a bit of a shame that Vlad has gone, because in Bergamo, Vlad did a workshop on CTEs, and he technically explained perfectly how these work internally. I don't know if I got all the details right, but I think you should get the idea. So don't blame me if it's not 100% what the server does, but it looks something like this. Introduced by this keyword recursive, the server knows that he has to do some preparation or pre-processing on the actual statement before it can execute it. So it's actually a three-phase process. It's analyze, transform, then prepare before it actually gets executed. So first thing that will happen is that I did this a bit symbolically here. So PA is the parent select and CH is the child select. So first the parent select gets transformed. There's some nitty-gritty details that are happening here that happen when you have complex CTEs with multiple CTE joins and stuff. Basically what it does is that it transforms all the non-recursive members of the CTE into this parent select. So then comes the preparation of the child select, and actually this gets really transformed. So what the server does inside is not what you tell it to do. It doesn't do a join. it really goes and takes away the recursion from this recursive definition, because that way it can't be executed. So you really flatten that child select. So what the server basically does, it takes this part of the child select, the join, which joins on the parent, gets rid of it and replaces it by a where clause. So now you see we have a simple parameterized query, which is non-recursive because it's just the select of the children with a new parameter that the server makes itself. And then it just goes and prepares both of those statements, which are now rather simple. They're just plain selects, and goes on executing it. Okay, so ready for execution time. This slide will get a bit full, I'm afraid, until it's ready, but I hope you can follow along. So first thing that we do is we execute the anchor query. So we get back the parent node's data and send back to the client. Then for every result row that we get, which is only one in the first part, because we only have the root node, it gets sent back. Then this result set is pushed to the stack internally in the Firebird engine. And now we enter the child part. So we'll execute the child select, and you saw that we replaced this join with a where clause. So this is where it takes the ID param of that where clause and fills it with the current ID of the parent. And then it gets a result set back, because you can have 10 or 15 children at that level. And for each child, it will call the second step with the current result set from that child select. So this is really the recursion inside the server. So you have one result set for the top, you have the second result set, and we take the current row of that result set, and with that we'll call this, and from here on it goes the same way. It sends back that client, that first child it finds to the client, and again pushes that result set to the stack. It re-executes the child select, but now with our current child ID as the new parent ID, because we're one level down. And then it just recurses until it hits the bottom of the tree where there are no more childs left, because then you have this result set empty, so it will skip this. So once we hit the bottom, we go back up one level. So this is actually the unwinding of the recursion, which means that we go back to the level that we were before by popping the result stack that we have on the stack as the next, back from the stack, and then we go to here with the next row of that result set. So this is actually just a plain loop. This is no recursion call. This is just a loop through a level of children. So the next slides, I really wanted to make one of my own, but I saw Vlad's presentation, and he made such a beautiful graphic, and I said, like, I can't do this any better. So I just wrote him an email, like, Vlad, you did this nice graphic, can I have it? And he just sent me the whole presentation, was kind enough to allow me to use it. So this next one is actually by Vlad. Shame he isn't here, but he knows I'll show it, so. This is actually what the server does with all those result sets. So you see, we have the first parent select that just gives back one result, and then it pushes that to the stack, goes to the next one, and first gives back the first result from that. And then it just recursively calls with this department now, calls this select, which is the child select on that level, and it will give back those first four, because for everyone it tries to find children, but it finds none until it hits this one, and this one actually has children. Here we have this red 110. So these are returned. And then we go on with this one, and this one has this, the arrow is a bit behind here, but you can see that this part of the select comes actually from this level. And so because we're doing this recursively, you get all the results back in just the normal tree traversal order that you're used to. But the thing to remember is for every recursion level, you have one prepared statement in the server. So if your tree isn't very deep, it can be very wide, that's no problem. But if it isn't very deep, then this is very efficient. Because you have only a couple of statements that are actually the same. This child select statement gets prepared only once, and it just gets filled with this ID parameter and gets re-executed. So that's what makes these things very fast. Okay, let's have a look at some real-world examples. By the way, I forgot to mention, if you have any questions in between, feel free to ask. No problem. Would be nice if you had some questions. Otherwise, I may have some time left at the end. But we can eat some cake if we don't find anything else to do. So, okay. As I mentioned right at the start of the session, this session is really about this. So, we're making some marble cake now. The thing with this simple piece of food is that it's really a recursive structure. Basically, it consists of two cake mixtures. You have the dark one with the chocolate, and you have the light one with the vanilla flavor. But this is both actually the same recipe. It's just one part of the recipe gets chocolate added, and the other one gets vanilla added. So you have one recipe that's referenced in two sub-recipes. And then we have a chocolate icing on top, which in itself is, again, a recipe. And so this is like a Lego kind of system where you have small sub-recipes that you can piece together to bigger recipes. So just for the non-English speakers here, some material definitions. We'll have some yolk, obviously, some egg that you need. We have sugar. We have flour. This flour, not this flour. Actually, in the Dutch language, it's really the same word. I find that very confusing. Okay, then we have obviously some butter, milk, some baking powder, the usual stuff that you need to bake a good cake. And then we have those flavors that usually you come across in only one of the sub-recipes, but they can also be in several sub-recipes. So let's look at the data behind this, so you can follow along with the examples a little bit better. Actually, this is what I said in the introduction part. This is a classical heterogeneous tree, because we have raw materials, and we have sub-recipes, and we have recipes themselves. So here I have my list of raw materials. It's pretty simple. It's just an ID, and I give it a material number, and obviously a name. That's about it. And then I have the recipes. So this is just the head information for the recipes. And you can see here that it's quite a lot of recipes, because I made two versions of that cake. The one version uses the vanilla cake mixture as one recipe, and the chocolate cake mixture of another. And this version here, the version 2, is the one that actually uses a sub-recipe for both the brown and the white mixtures. And obviously we need some head data for all the sub-recipes. So we have the chocolate cakes mixture, vanilla. We can also have lemon-flavored icing. You see that too, that's the white icing on top. We have the chocolate icing. And then we have this basic mixture with a sub-sub recipe. And then we have the recipe positions, which is really, if you think about, let me just see what slide that was. 14. This is this concept. You have one table where you store the links, either to a recipe or to a raw material or to a sub-recipe. And so this is actually the recipe position table. This is this link table. So in here, there's some denormalized fields. Maybe I should show the trigger on that. Normally you just need IDs and reference IDs, but that makes it pretty hard to follow what is referenced by what. So I just made this trigger that whenever you update or insert into this table, it will select the names and the numbers of the recipes and raw materials and just put them in this reference table so you can see directly what you're referencing. They're actually not needed and not part of the recursion of the tree structure, but they make it a little bit easier to follow. So that's why you can see here. Oh yeah, one more thing that I should mention, I have a sequence number. So when I have multiple child nodes, I can have an ordered number of how these sub-recipes are traversed. So let's look at the more interesting fields. It's a bit annoying when the screen is so small, you have to scroll around all the time. Here I have a marker whether the entry is a sub-recipe, that's a 1, or it's just a raw material. And let me go here. So this is the, this field is actually here, the pointers that are pointing to the other tables. This is the ID of the raw material, or the idea of the recipe, if it's a recipe. And most important really for the recipe is the, just to hit the right pixel and it works. So this is the percentage. So if we try to follow in this one the I'll just show the select, that may be easier. So, okay. First, just to compare, I've also made this as a recursive store procedure without a CTE. Because you can mostly do anything that you can do with recursive store procedures, you can do with the CTEs and vice versa. So just to compare, here we have the classical recursive store proc that selects the parent data and loops through all the child data. And now here is one thing, because it's a heterogeneous tree, we have to make a decision between two things. Either I hit a node that is a sub-recipe, or I hit a node that is a raw material, so I'm at the end. So if it's not a sub-recipe, then I just select the data from the raw material table and suspend that. And if it is a sub-recipe, then here I have the recursion call that actually calls the store procedure itself, but with the ID of another root. So this is actually a different tree, but I'll give it back as if it were one big tree. So, see what that looks like. The second version of my recipe was the ID 7, so this is our root ID for all the examples. Just let that run, and you see I get on level 0, I get the head recipe, which is the entire marble cake, and then on level 1 I have the chocolate cake mix, which consists on level 2 of the basic cake mixture, and on the 4th level this is the list of raw materials for the basic cake mixture. And on that same level 2, I also have the chocolate flavor that just get added to this basic mixture. And below that we have exactly the same thing, just with the vanilla. So again, same basic cake mixture, that's exactly the same tree as we have here, but it just appears twice because it's referenced twice in the data. And it will end up with the vanilla flavor, of course. And then we have the icing, which again consists of a few raw materials, mostly sugar. And what you sometimes see is that they put some sugar right on top of the cake, on top of the icing. So there's an extra position of just sugar that gets added at the end. Sugar baby. This is another example of a model cake. You can do them in all sorts of variations. And here you can see that this one has at least 5 sub-recipes. I couldn't count the colors all right, but I think it's about 5. And now the thing is that each of those recipes can have a different percentage of sugar inside. And this may look like a funny exercise, but actually if you're selling these cakes, this is a real-world problem that you have. Because actually, I brought some of those cakes here. If you read those little informations on the bottom, every food manufacturer needs to supply not exactly a list of ingredients, but at least some nutrition facts on the food. So you have to really calculate how much sugar do you have in that entire cake with all those sub-recipes and different percentages of sugar on those different levels. So that will be our first question that we want to get answered with the CTE. What percentage of sugar do we have in the entire cake? Next question. Now, okay, I say I want to make that cake. I'd like to have 5 kilograms of cake. How much sugar, how much butter, how much milk, and so on do I need to make these 5 kilos? And the next one, and this will be the final example, and I must admit that the solution to the CTE is by Philip Markowski. He sent it to me. I was sending him the examples, and he was like, this is an interesting problem. I'll try to solve it. And he actually did. He solved it. And I don't really understand how it works. But it works. Okay. Let's go back here. First of all, we will do a basic CTE. And I mentioned already that they can get rather long, but I hope this still works. You can still read it. Try to make it a little bit smaller so it will fit on one screen. So it basically, this select has 3 parts. It's a 3-part recursive CTE. First, we obviously have our parent select, which will select just the head recipe. Then we union that on a second CTE, and this one is, what's my tree called? Or what is it? Oh yeah, there. There's the join. So this is my recursive tree, and here I select the raw material names, and my join condition is that this is the parent link. So my ID recipe of my child node is the ID of the recipe that I'm just coming from, my parent. And second condition is that the flag recipe must be a 1. So this is the part that traverses the sub-recipes. Actually, this example is wrong. It should be like this. Damn. I was just wondering, it's raw materials, not recipes. So this is the raw material part, right? You can see it here. It selects from the raw material table. And this is the join condition. And so the next part is the recursive traversal of the real sub-recipes, which is basically the same construction. It's also a join on the R tree, but with the condition that it is indeed a sub-recipe, and you see that here we select from a different table. So that's how you can do heterogeneous selects within a single CTE quite easily. And then we just go and select everything from that CTE. This isn't what I expected. I think this was right. Oh, damn, yes, of course. Sorry, my fault. This is the RT, this is the tree. So the parent of my node must be a recipe. So this is really the way it works. Ah, that looks better. So here you can see the recursive traversal of that recipe within a single select. You can see it actually now has 3 plans because we have 1 parent select and 2 child selects, but it's basically the same as what you saw on the other slide with the recursive resolving. Okay, let's have another example. You saw that this result set that I got was just a plain flat list, and I always like to have them indented so you can see the tree structure. This is actually quite easy to do with CDEs, because the whole trick is that you, in the first part, you select a 0 as the tree level, and in the second part, you just take this from the recursive join on the master node, you take its tree level and just add 1 to it, and so you get a recursive tree level. The next thing I did here, to make it a bit more structured, is that I calculated a table of contents index, like you would have with chapters and subchapters in a Word document, for example. So, same trick. I'll just start off with an empty string here, and for every child, I will just take the running order, the child order of the raw material or of the recipe, cast it to a string, and put a dot behind it. I'll do the same thing here. So, what this gives me, I get rid of all the other fields that I don't want here, is you get a nice table of content index. So here you can really see that these are all on the same level, these 4 guys, and this one is on the same level as this one. And right at the end, we should have a single position of sugar, which is on the top level. Okay, so that's quite nice. But it's not really what we wanted. Oh yeah, that's one thing I wanted to tell you. There's one thing that really applies to all unions. It's not specific to CTEs, but you should really watch that and take care of that. That's string truncations. The next thing I tried to do was add in a column where you can see whether it's a recipe or raw material. So for the recipes, I just gave back the word recipe. And for the other ones, they just return raw or sub-recipe. Now, what happens, I should copy this to IB Expert, really, because it shows the error message better than my tool does. When you do this, you get this. And it took me quite a while to find out what's going wrong here. Once you know it, it's actually quite simple. You see here, this is the first part of the select statement, and as with any union, this defines the length and the data type of the fields that you return. So, if I just give back the word recipe here, then Firebird assumes that's a six character long field. Character field length 6. Now, unfortunately, the word sub-recipe is longer than 6, and so as soon as it hits the first sub-recipe, it goes boom. I can put that into 6 characters. So there's a simple trick to avoid this. You have to cast the first result to the maximum length that you expect when you traverse the tree. Same thing, and now it just works. And you have this additional information like it's raw material or sub-recipe, whatever. Okay, next try. Percentages, that was what we were after. So the first thing I did was I just give back the level percentage of each raw material. So inside a sub-recipe, what percentage does it have there? So obviously the first one has 100, it should be 100 really, and we'll do some check selects later on to verify that it's really 100. Most common mistake when you do recipes, you have a recipe that ends up in 92%, and everybody's wondering like, I don't have 5 kilograms of cake, how comes? So here you can see that our chocolate cake mix in this recipe has 40% of the entire cake. And so does the vanilla cake mix. It's also 40%. And down here we have the the icing, which has 10%. And finally, we add another 10% of sugar that we just put on top. So that gives 90% on that level. Now, if you take this level, for instance, these 4 were raw materials, then it's 30 and 20, it's 50, it's 60, so this is 100 too. And the basic cake mixture is made out of this, 90%, and 10% of this chocolate flavor. So it all fits in. But obviously, this information is rather useless because we can't calculate with that. So, next, we're adding another column that gives us the overall percentage in the entire cake, which is, again, quite easy since we're thinking recursive. So what I really do is my top node has 100%, and for every child node, I know its relative percentage to its parent node. So I just multiply that percentage with the overall percentage from my parent node, and in theory, this should give me the relative percentage. Let's see if this works. Okay. I hope you can read the numbers. They're a bit tiny, but... So, first one, we have overall percentage 100 and level percentage also 100. For the first level sub-recipes, this is also the same. But now we get a sub-sub recipe, and we see that the 90% of that sub-recipe is actually only 36% of the entire cake. And since this just recurses down, you can see that in this sub-sub recipe, we have 20% of sugar, but this makes 7.2% of the entire cake, because it's just calculated recursively. So, now comes what I mentioned earlier on, what is one of the real strengths of CDEs. Oh, actually, this one is still quite simple because you can do just a stupid select on the results of the tree and just tell it to sum the overall percentage of all the nodes that are named sugar. So this gives us 28.4% of sugar in the entire cake, just one select. That's pretty handy. Okay, what do we have here? I just want a raw material list. I want to know how much sugar, how much butter, how much whatever do I need. So I just do another select from that same recursive tree data and just do a group by the distinct number, the raw material number. And I only want the raw materials. I don't care about the sub-recipes. Now I just want to go down to the real raw materials. So just group this by 1. And as you can see, we need 28.4% of sugar, 7.2% of egg, and so on. And this will just list it up quite nicely. Because no matter how often one raw material takes part in that tree. Sorry, is this example? Well, we can just check what happens if we don't do it. I have this sugar several times because it occurs in several sub-recipes. So if I... Oh, you're probably right. That's true. Let's try it. Oh, yeah, damn. Yeah, you're right, actually. So this thing is not needed here. But it doesn't harm either, so. Okay. Let's go on. So we saw this, actually I can, now that you say it, I can make this a lot easier too. Oh no, I think I need the aggregates there. Yeah. Okay, so this is what I said before, that you can chain those CTEs. So this is basically the main statement of the last example. And now I want to play a little bit with the results of that thing. So I just define another CDE that I call material list, mat list. And I just take this exact select and just put it into brackets. And I have another CTE. And now I can do a select from this second CTE and even join it on the raw materials because I want some lookup data. I don't really know what I'm looking up here. Oh, it's just the name, yeah. The tree will give this back by itself, but you could make the upper select a bit simpler so it will just return the IDs and then you can here join on the other stuff. So actually in the main statement, we don't use the recursive tree at all, but we use the second select, the second CTE, and that again uses the recursive CTE. So that's what I said earlier on. You can drill down. You can start off with your data in the form you need them, and then just boil them down to what you really want in the end. So this is basically the same what we had before, but it just adds the joined material names. Okay, so the upper part is always the same, so I'm not explaining this again. Now, I want to make sure that we actually have 100% of material in our recipe. So I just leave that there and just add another CTE, which basically is the same select that I had in the example before. You don't need to do this with CTEs all the time, but it's just a lazy way of getting to the point where you want to get. It's just, you have one sub result that you can work on, just stuff it in a CTE and go on with select from that CTE. So here you can just do a sum from, you saw on the other example that I got the percentages of all the materials. So here I'm just doing a sum from that checksum CTE. And this should give 100, which is good. Oh yeah, now we're up to this one here, question 2. We've only had percentages so far, so I want to know how much kilograms of raw materials do I actually need. And this is quite simple when you have the percentages. You just do the simple percent calculation. So this is my target weight. And again, this all is one select statement. So what you can do is just replace this by a parameter, prepare that statement, and stuff in the kilograms you want and just re-execute it. So but here in this example, I just want to list for 5 kilos of cake. Okay, there you go. The percentages, and you have the kilogram amounts. So, how much time do we have left? No, we have a couple of minutes. Now to the final example, or the final question. What can I do if I only have like 1 kilogram of sugar? And actually this is what Philippe sent me, and I don't absolutely get what he does here really. What he basically does is he takes that same select with the percentages, and then he uses another select that will give him the amount of sugar, or actually it will use the amount of sugar to produce a result, which he then cross-joins with the select of the other stuff. And I must admit I've never used cross-joins before, but it's like matching two records. We have one result set and another one, and the cross-join will match exact pairs. So it will match from the recursive CTE select, it will match the record that returns the amount of sugar that I have. That's basically what happens. So if you execute this one, oh, double precision fields here. It gives you two informations. First, this is my condition. I have 1 kilogram of sugar, which is matched. it will give me the exact amounts of the other ingredients that I need, and it will also give me how much cake it will give me in the end. So that's 3.5 kilograms of cake. Okay. We have a few minutes left, but maybe we can take a look at this. Just a little attempt to do a speed comparison. It doesn't work really well here. The results are not so obvious because my laptop is rather fast and there's rather few data in the database. To get this to work at all, I just made a second version of this file system table. And this actually contains not only the few records that we've seen in the other examples, it contains quite a lot of records actually. In all, it's about 67,000, which is a dump of my MP3 library, of the file structure of the MP3 library from 2 years ago or so. I'm more than 100,000 now. But anyway, it's the classic recursive structure as you know it, with the ID master and master ID link. And to make it comparable, it is also a nested set. So I just run this store procedure that will turn my normal tree into a nested set on this table, which doesn't take awfully long. It goes quite fast, actually. It adds in the tree level, and it adds in all the LNR values. So just so we can compare the results, really. So, first thing I did was the classic top-down recursive store proc, but just with the big table now. And, oops. So we can just, I just have to look what my root condition is. First is ID 1, ID master is 0. Okay. Oops. So we just do a select from SP Francis big dump there, and ID root is 1. Oh, yeah. We'll just run this. Of course, the first results appear pretty fast, but if I go right to the end, you can count like 1, 2, 3, 4, 5. Okay, it's about 5 seconds something. Sorry? I'm sorry, this is just the personal edition. I don't have the pro edition. Is Holger here? No, he isn't. Okay, I'm using DB Workbench. Yeah, but you can take a look at the plan analyzer. I mean, the results are just as expected. I checked them with DB Workbench. It does the usual reads and stuff, so no surprises there. Next, let's do this same thing with the nested set. Well, this is just again with the trick, so we get a nice tree-level structure. We run this, and now you get this nice directory tree. We run down to the end, and it's 1, 2, boom. So that's a lot faster than recursive store procs. Whether that's relevant to you, of course, depends on how much data you have in your tree. I mean, 60,000 something records depends. It can be a little compared to what you have. It can be an awful lot. So if your trees are much smaller, usually, then I wouldn't go to the trouble of using nested sets. But if you have like 5 million records in such a tree, then the nested sets are definitely very much faster. And last but not least, we also have the same thing as a recursive CTE. Let's go here. So, same concept. I select the define the recursive tree, select parent node, union all, select all the child nodes, and I just stuff together the indent field, so I also get this nice tree structure. hit execute, and now it's like 1, 2, boom. So you see it's almost as fast as the CDE. It's actually, I can't really measure the difference here on my laptop with that amount of data. But obviously, since the nested sets is just a plain select, as bigger the tree gets, as bigger you will see a difference. Because remember that for every level you have, you remember that one slide from Vlad? For every level you have a new statement. You have a stack. And that's one thing to really remember. Nested sets are very effective when it comes to server memory, because you have just one plain select statement that is returned, while with CDEs you do have this pushing of result sets to the stack, and this all takes memory. May not be much, depends on whether it's a problem to you or not, but just some things to keep in mind. Okay. I would say that's about it. Any questions? Come on, can't be so lazy with questions.
Have you any graph for compensation number of before we compare?
Sorry?
Store procedure with CTE?
What do you mean, the memory result?
Speed result. The result of number of reports to time to...
Really, I didn't really measure it. I just counted them, like I did just with the seconds. But if you have the full version of IB Expert, you can see the plan analyzer results, and DB Workbench has that too. And you can really, but I don't have the full version on my laptop here. Otherwise, I could show you. But yeah, yeah, but you can have all the database. I will make it available certainly to Holger, but since I know that he's always a bit late behind on publishing those stuff from conferences, I will probably put it up on my website, so you can just send me an email and download the demo database there and just play around with it. And then you can see for yourself with the execution plans and stuff. You have one question? Oh, yes. Oh, good question. Yeah, I think it's 1,024, if I'm not mistaken. It's somewhere around 1,000. Is that? 23, okay. Yeah, okay, yeah, right. That doesn't count. So, good question. With CTEs, you can go 1,024 levels deep in your recursion. But if you want my personal opinion, if your tree is 1,000 levels deep, you have a problem in your data structure. That's probably then what's, what do we have this? Then it's very likely that your tree looks like this. Then you can easily reach 1,024 levels. But if you have this one, go figure, it's 2 to the power of 1,024 nodes that you can stuff in such a tree, if it's a binary tree alone. So you should never really hit this limit in practice. Okay, any more questions? Okay, then I have a question. Do you want some cake? Okay, then come along. And thanks for your attention.